derived for general form, right? When this is f some function fg of more general, right? This is a specific case. So if we know how to solve a general case, then we don't have to go through the whole process. We just use the final representation. So this one fits that situation, right? This is exactly the model problem we discussed. Yeah. So C is 1. The L is pi from 0 to pi. You see the length. Initial condition. The f function, that's a g function. So the solution, final solution is this form, right? We already discussed. Final solution will be this form after the analysis. So now we just need to determine the coefficients. That's all. Yeah, coefficients.
So, okay.
Yeah. How to calculate the coefficients an and bn. An I erased. You have it on your notes. Yeah. So bn we still have it. Yeah.
So it'll be 2 over pi.
Yeah. So let's write it down. So for this, using the two initial conditions, right? We can.
So an is 2 over L, well, in this case, 2 over pi.
So this one, in case you don't want to look at this, you can also just directly substitute. That's fine. That's fine. You just directly substitute because you have solution in this form, right? So this function, just put a 0. You can see clearly when t is 0. Okay, let's just write. An. When t is 0, that's gone. Right, when t is 0, so this is solution, this is gone. That is 1 times an times that. That's it. Should be equal to that sine cube. Sine cube. Yeah, for ln x between 0 to pi. Yeah, but eventually you are actually comparing this series with something. But this one can be reduced. The power can be reduced if you use the product to sum formula, the power reduced form. So you can check this one. I will save some time. I will give you reduced form. This is actually and 1/4 sine 3x, 3/4 sine x. Yeah, so this one, after you do the product to sum formula or the power reduction formula, that can be written as this using trigonometric identities. Yeah, so this is that. This one is we keep it. Certainly, you can use the formula, integral formula, right? You can calculate, but even without those integral formula to calculate an, we can compare term by term, right? You're looking at the left hand. This unit series equals that. You see this L is pi, right? L is pi. So actually the pi, and this is actually nx. So this is sine nx an. Because this. So you immediately know you have only 2 terms in that series in order for the left to be equal to the right. Which term you should have on the left? This one when n is what? 1. Yeah. So just a1 is not 0, right? What is a1 value? 3/4. Yeah, 3/4. Then here's another a. A sub n is non-zero. What is it? Which term? 3, yeah, because that's 3x. So a3 is not 0. And the value? Yeah, -1/4. So this time we didn't use the integral representation to calculate the coefficient. We could, right? We could have done that. But it's not necessary. Actually, we found. But all the others will be 0. an will be 0 whenever n is not one of those two. Yeah, if n is not 1 or 3. So all the others will be 0. We found the coefficients based on the first initial condition. So one more initial condition. Yeah, so let's look at this. Solution will be this form. But the L is equal to pi, right? L equals pi, so this is actually cancelled. So this is actually this one. L equals pi, you see this is just this. L is pi. Yeah, so the solution final form, U is this form. Yeah, that's U. So let's go to the second initial condition to determine the remaining coefficients, the B's. Take the derivative. That will be sine, right? It will be drop. Then this take the derivative, you get cosine. Cosine, then you have NC, right? As a part of the coefficient. NC. C is 1, right? In this problem. So C is also gone. C is 1. Yeah, just put a specific value. So it's actually just NT. So take the derivative, which get cosine, which is n. N times Bn. And cosine nt when t is 0, right? It's 1. So just this. And then sine nx. There's no sine function outside. So here's the sum. N from 1 to infinity. This function should be equal to what?
Sine 2x. Sine 2x.
Sine, yes, that's a g function, sine 2x. Very good, yeah, sine 2x. So that's the second initial condition. This, when derivative when t is 0. This u, take the derivative with respect to t, right, when t is 0, equal to the g function. Let's do comparison. This is easy to compare.
Oh, that's okay.
Yeah.
So,
B2 equals 1/2.
yeah.
Yeah, B2. Yeah, so only B2, you see when n is 2, right, sine 2x. Compare, that's only one term on the right hand side. So only B2, from here you will conclude that B2 is 1. So B2 is half. B2 is half. And all the other will be 0 when n is not equal to 2. Yeah, so we got all the A's and B's in this problem. So now let's finally write our solution because we're almost done. We know only a few are non-zero coefficients. Almost all are 0 coefficients. Yeah, so then the series will be easy. It's a finite series, right? It's not an infinite series. So let's write it. The U. Okay, let's get only the A1, A3. A1, so which is 3/4. 3/4 sine. That's a 1, right? Sine x. That is a cosine 1t, cosine t.
Then B is 0, so it's gone.
What?
B1 is 0, so we're done with that.
Yeah, we don't have that yet.
Okay.
And then let's take A3. A3 is this. What is A3?
Negative 1/4.
-1/4. Sine
3.
3x And then let's take a B2, the term with B2. B2 is half. So we should have half. This will times that. So sine, when n is 2, that's a 2x, sine 2x, sine 2t. Okay, that's all. So we have only 3 terms. Yeah, in that each one is a product, right? Product of x, function x and function t. So this is a classical solution because it's obviously twice differentiable, right? It will satisfy the PD and you can verify this expression will satisfy all the conditions. So yeah, we discussed the general case and the specific problem. Today, if you want to modify the boundary condition, you can try it yourself. Actually, on the book 5.3 related problems will be number, I think the exercise for chapter 5. Chapter 5, I think number 2, number 3, number 4 are wave equations. Yeah, if you want, you can look at the problems. Yeah, because on the book you will solve this topic. You can look at another example with the normal boundary condition. Okay, that's it for today.